Okay, so hopefully you guys have gotten that balanced chemical equation done for this one. You can see that solid magnesium is going to react with an iron 2 nitrate solution, so therefore the aqueous state. You can see the balancing of the formula. Magnesium nitrate and iron should be the products, as you have two cations to switch places. This one's a little bit unique though. You can see that it's asking which will be the limiting reagent. We don't know. We've got two starting quantities, and now, very realistically, we do not know which one runs out first. In a lot of chemical reactions, you have your initial concentrations of your solutions and your certain amounts of reactants, you mix them together. But unless you did the pre-work and the stoichiometry to know which one was the limiting reagent, you would have a hard time predicting any sort of quantity. You might have to do a lot more work trying to deduce this. So a lot of times what we'll see, and these will be in the harder questions, not every question we give you will be like this, at least not in high school. University is another story. But we'll give you two starting quantities, and you will have no giveaways in the questions. There's no word as limiting, there's no word as excess for any of the two individual compounds or solutions. So what we have to do is really just do a test. We have to see stoichiometrically which one should run out first. And if you recall, the limiting reagent is the one that we say will produce the least product. So what we can do is we can run stoichiometry a couple of times, and we can figure out which one will produce the least amount of product. It does not matter which product you pick. All right, so long as they're the same for both tests of your two reagents, then it's just fine. So I'm going to figure out which one produces the fewest number of moles of iron. That's really all I need to do. Which one produces the smallest amount? I'm going to work with moles, since that is a chemical amount, and it means I have one less conversion step to do. Okay, so which one produces the least amount of iron? Let's start off with this one. If I have 4 grams of magnesium, I need to first convert this to moles before I can do any sort of stoichiometry. And so grams would go on the bottom, moles up top. 1 mole of magnesium from your periodic table weighs 24.31 grams on a scale. Now the balancing in this one was nice and easy. Because we're dealing with limiting reagent, I didn't want to give you the extra problems, so this was a 1-to-1 to 1-to-1 balancing, which is nice and straightforward. So magnesium on the bottom and iron up top, and you can see 1 part iron for every 1 part magnesium, and magnesium is now eliminated from my factor label method. I now have, in this one, moles of iron, and so, whoops, that's the wrong symbol now, isn't it, folks? Put an equal sign here, and you can see that you get 0.1645 moles of iron. Now, when I test iron to nitrate to see if it produces more or less, I'll be able to compare the two quantities and figure out which one ran out first, because one of these stops the reaction by running out and limits the amount that I can get here, hence the term limiting reagent. So let's check your 6 grams of iron nitrate. And so I have grams. I need to turn that into moles. So I have the same molar mass fraction here. But 1 mole of iron nitrate is much, much heavier. And it's 179.87 grams. And so grams now go. I now have moles, so I can do my mole ratio. And again, for simplicity's sake, there's your iron nitrate. There's your iron, and you can see the same 1-to-1 mole ratio. But that does eliminate iron nitrate from the solution. Now I have moles of iron, and when I check this one out, I get 0.03355 moles of iron. So which of my two reactants produced the least amount of iron? You can see that this one here produced less iron in the end, Therefore, iron 2 nitrate is the limiting reagent in this problem. Yes, I realize that some of this is a little bit tedious, but this is realistic. When you're measuring out and weighing out quantities, we do not know the molar counts, so chemistry does demand that we do some predictive stoichiometry to see which one should limit the reaction. We can later run this reaction in lab and we can see if we actually come anywhere close to these values, and then we can get into the other stuff we talked about in the previous video with percentage difference, percentage yield, and so on and so forth. Okay, so we test 2 starting quantities against 1 finishing quantity to determine a limiting reagent. Another question I can ask from here is, how much magnesium should be used to ensure a complete reaction? If iron nitrate is our limiting reagent here, and we're cool with that, then there is a certain amount of magnesium that I should use that is economical, that is still sufficient, but not wasteful. Okay, so what we can do is figure out if 6 grams of iron 2 nitrate is completely consumed, what mass of magnesium do I actually need to use all 6 grams? So we run stoichiometry again. It is repetitive, I admit tedious, but necessary. There is no way around this until we somehow develop a way to count atoms on some sort of device in a chemistry lab. And that isn't happening anytime soon. So we start with this one. If I start all over again, I now have 6 grams of my iron 2 nitrate. I need to convert that to moles. So I'll use my same mole fraction, grams on the bottom to cancel, moles up top, and 1 mole has a weight of 179.87 grams. Awesome. Now I'm in moles of iron nitrate. I can now redo my stoichiometry, but now I'm doing it between my 2 reactants. So, iron nitrate on the bottom, magnesium up top, and you can see in this one I kept it nice and simple. It's a 1-to-1 mole ratio, but that does get rid of the iron nitrate from the problem, and I now have moles of magnesium. Probably not looking for moles here, I'm looking for mass because I'm trying to figure out how much I realistically needed, and so I should do one more step here and figure out the mass. Moles are still here in the numerator, they come down here, grams up top. 1 mole of magnesium is 24.31 grams on your periodic table, and now I have magnesium measured in grams. And when you run this through your calculator, 6 divided by the molar mass, the 1 and the 1, decide if you want to use them in your calculator or not, multiplied by 24.31, works this out to 0.8109 grams of magnesium. Now this is the absolute minimum amount. This is the 1-to-1 molar ratio that we would use, but unfortunately this would be very, very slow. Remember from the previous lesson we talked about an excess reagent rule of adding at least 10%, and so I'm going to multiply this value by 1.10 or add 10% because I want my excess reagent to still be in excess, just not wastefully so. Like, look at this number, 0.81 grams. We were wasting 4 grams of this beforehand. It'd be in the sludge and the mix. What a waste of money. What a waste of supply. What a waste of material. So a 10% excess rule is what is expected. So 10% over 1 is 1.10. Multiply that through, round your answer, and you get 0.89 grams of magnesium as what you should probably measure out on the scale in lab. You've just saved 3.11 grams of magnesium. It's still in the chemical stores. Your boss isn't mad at you for wasting all this magnesium. You're a hero. Okay? So 10% excess rule was kind of what we see with the should. And so take that. Remember, stoichiometry will always predict the minimum or smallest amount that can be used by the quantities you have. Again, my sign off here is I hope this makes sense to you. I hope this is working out. I have a few different examples, percentage yield, percentage difference calculations that we'll do in the next couple of examples, and we'll come around to, I think, one more limiting reagent problem before these examples are done. Okay, one more video to go for lesson number 2, and we'll see if we can't get them through them in the next single video.